Hello, my name is Jamie O'Reilly. I'm the author of this article in the Journal of Neural Engineering, and I'm going to narrate the video abstract for you. The sound that you just heard was presented to two groups of laboratory mice, a conscious group containing 17 animals and a urethane anesthetized group containing 14 animals. Both groups of mice were also administered a sub-anesthetic dose of ketamine, which is known to influence the auditory response. While presenting these sounds, electrical signals were measured from above the primary auditory cortices, and from these we obtained the cortical evoked responses. The audio stimulation was represented using a square pulse for the stimulus, where the low value represents sound off, the high value represents sound on. And there was also a second input representing the state, where the four groups each had a different state value. This input representation was passed to a recurrent neural network as the input, and the labels for the recurrent neural network to model were provided by the cortical evoked responses. And then the RNN model was optimized to generate the waveforms matching the cortical evoked responses, or the event-related potentials. This graph shows the four different model input conditions. So we have the anesthetized mice after administering ketamine. They were represented with a state value of 0.25. The anesthetized group was represented with a state value of 0.5. The conscious group after giving ketamine was represented by 0.75, and the conscious group was represented by 1. Otherwise, the auditory stimulus was represented in the same way for all four groups. And these were the input conditions for training the model. And after training the RNN model, you can see that its outputs, shown in the solid lines, very closely match the event-related potentials, showing with dotted lines for both the anesthetized group and the conscious group. After training the model, I ran this simulation where the state condition input was varied from 0 to 1.25, going beyond the range of the training data. And this can be used to evaluate the changes in event-related potential that occur between states. The N1 peak amplitude was measured and can be plotted by state, showing a relatively more linear response than the P1 and N2 peak amplitudes. P1 peak amplitude was almost 0 microvolts for the anesthetized group, but shot up and became positive for conscious animals. And likewise, the N2 peak showed a negative sigmoidal characteristic. The highlights of this article are that it provides a new technique for simulating event-related potential waveforms. This can be used to characterize changes in ERP morphology between states, which could equally be applied to human data, and the data and code associated with this article are openly available.